Hello everyone, my name is Namugamata and my project is an AI model that succeeds to be specific coffee seeds. So my presentation is going to flow as follows. I am going to have my heat maps, the correlation matrices, the box plots, feature independent plots, the outliers, the patterns of interest, the trends in time and space, exploring data, and the operations of my data set. I'm going to explore, I'm going to clean, I'm going to split it, and then I'll tune the hyperparameters, and then evaluate. I'll have my evaluation. So, okay, let's look at heat maps. So what are heat maps? A heat map is a graphical representation of data where the individual values contained in a matrix are represented as colors. So why do we need heat maps? They help us identify patterns and trends in the data. They help us identify the outliers and anomalies in the data, and helps us visualize the results of a machine learning algorithm. As you see down, I have a matrix, a heat map. So why is that heat map all pink? Because I cannot draw a heat map using images. Images are looked at as one. So I will not have those divisions of different colors. That's why I only have an image of pink. When I look at the values inside an image, or when they're turned to, first of all, usually we deal with numerical. That's why we have the images are only giving us one color. So heat maps are not necessary we can't draw heat maps using an image data set. Then when you go to a correlation matrix is a square matrix that contains correlation coefficients between several variables. So each element in a matrix represents the relation or correlation between two variables. And the matrix is used to visualize the relationship between these variables. What am I talking about? When I have my correlation matrix, it's helping me visualize the relationship between variables in that matrix. Yes. So why it's not possible in my data set? My data is image, or their images. So I only have my image mapping to a label. So it's going to be very difficult to be able to sort or to plot this, because I only have one column. The relationship is between those two. So what's the relation? What's the use of a correlation matrix? A correlation matrix helps us to identify the variables that are strongly correlated, and it also helps us identify multicollinearity in regression models. So when we go to box plots, what is a box plot? All these things are graphical representations of. Now here, our main emphasis is on numerical data. So a box plot helps us to display the minimum. So we're playing around with numerical data, minimum value, maximum value, the median, lower quartile. So as you see, there is no way we can actually plot a box plot in images, because how are we going to identify the lower quartile or the upper quartile or the minimum value in a data set? Yes. So it's usually used in those statistical things, data science. Yeah, so it helps us visualize the distribution of the data set. Then we move ahead to a feature independent plot. So what's a feature independent plot? It's actually also known as a scatter plot matrix. It helps us identify, it helps us know which variables depend on each other and which don't. So to be specific, when I'm looking at my data set, I only have, as I said, I have an image mapping to a what? A label. So actually these two are independent. The image cannot, I have an image there, it can exist alone. I have a label there, it can exist alone. Yes. So it's when I feed the image to the what? To the model, that's when it's able to attach a label to it. So technically speaking, these things are independent, because an image can exist alone, a label can exist alone, but feature independent. Given a data set with very many features, you can see those that depend on each other, those that do not depend on each other. Then we have the outliers. Outliers are those that data that's abnormal from the rest of the data. Take an instance. If we have a line of best fit, we'll have, but when you draw a line of best fit, we'll follow the plots. I mean, we'll follow the data that's where it's concentrated around there. But then if we have data that's so far from the line of best fit, that's unusual. So it's the use of these outliers. They help us to identify and analyze data points that are unexpected, because you can't have a line of best fit and a point is very far from the line of best fit. Then, yes, so it helps. It's also maybe an indicative of an error. It's helping us or an underlying problem in the data. Then we look at the patterns of interest. So in our data set, what are our patterns of interest? What are we looking at? Yeah, what do we want most? So if we're looking at a cluster, yeah, so we want that place that has the most data points. So that's what we're looking at, the relationship. So you look at your data and then what are you interested in? Am I interested in relationships between variables? Am I interested in the things that are scattered? So what is your point of interest? So it's a graphical representation of data that highlights the patterns of the trends that you're interested in. So it's also graphical and it cannot be plotted. It's usually for numerical data. So we look at the illustration of trends in time and space. So when you're looking at a data space, we're going to a data set, we're going to see if we change a variable's location, will each time and space change? So those are things we are looking at. Yes, so that's the illustration of the trends in time and space. So if we are, so now we're going to look at our data set. So we loaded our data set in our Jupyter notebook, and then I was able to load it. So this is it. It's the rows and the columns, the fields. So it has, this is what the data set looks like. Then I had to clean the data. How do I clean the data? We have to check out if this data has any null values or duplicates. So we looked through, so we did not find any null values. So we are cleaning the data. We are showing that we do not have null values in our data, i.e. it's good to go. If we had like null values or duplicate values, then we would have to drop them. So we'll go, since our data is clean, we have to go into splitting. So this is what I used to split. I have my root folder that carried all the images, and I had to split it into 3: training, validation, and testing. So I split the data, because inside the main folder, I have other folders for the different categories of the seeds: green, medium, light, and dark. So I had to work in such a way that when I'm splitting, I have to split them according to their labels as well and put them in the new folders for training, testing, and validation. So I split this data in a percentage of 70% for the training, 20% for the validation, and 10% for the testing. So that's how I split the data from the main file to the 3 different files. So this is still splitting the data. I can, if I'm to take you through the algorithm, or sorry, if I'm to take you through the code. So this is identifying that there are patterns, there are categories in my main folder. And then here I'm starting to put, like from the main folder, I'm splitting the data into the different categories, and I'm putting those categories in the training folder, validation folder, and the testing folder. Now, when I'm transferring these the images, I'm transferring them in a ratio of 7 to 2 to 1. So this is what it means. And then this is all going through. It's like a loop. So this is going to validation. This is for copying the files into the validation. This is copying to the file into training, and this is for training, validation, and testing. So I have to fit my model after separating. I had to fit my model. So it's a neural network. So it's most times you have the impression that you have to build very many layers for a neural network, but actually a few layers can work. I worked with one layer because my data is not a lot. So I was able to compile the model, and it was running. So this is it running because I have the training, the testing, and for it to run, actually, I'd forgotten to mention or the fact that we have to change our images and put them in a NumPy array. So that's one of the things that gave me a hard time because I did not know how to change it to a NumPy array. So once I found out, everything else was working. So this is it. We have our optimizer, which is we try to use Adam, then the learning grid. If we give it a learning grid that we earlier described when we go through, you earlier said that we described our learning grid. So you may give it a very fast learning grid and it will not actually train. So you have to give it like it's supposed to learn at a specific rate so that it's actually trained. So it does not memorize, but it learns. The model learns. So we have the evaluation. So we are supposed to evaluate our model. Is it actually what? Is it actually working? So here we are able to put images so that we see if our model is working. And then we talked about hyperparameter training. Actually, if I'm to take you back, hyperparameter training is mainly to do with changing and seeing if this model is actually fitting and it's being able to be trained. So our hyperparameter training in neural networks, hyperparameter training is mainly in this level. You're supposed to change these layers, play around with the layers till your model is optimal. So that's where our hyperparameter tuning, we play around. Then other things, we have the if I hold the cross validation, but here we're supposed to use, you play around with the layers. So that's our hyperparameter tuning, play around the layers and learning rate. Those are things you're playing around with. That's how you tune. And then evaluation, we are testing if this model is actually working. Yes, so when you see here, we have the training accuracy, the validation accuracy, So it was training, it actually learned. So that's your evaluating. So that will be it for today. Thank you so much and have a lovely week.